Cool. Okay, so we've got people starting to file in. So yeah, welcome everyone to the 38th Climate Sensitivity and Cloud Feedback Virtual Symposium. We have two speakers today. So first we have Harry Mutton from the Met Office, and we also have Kate Marvel from NASA GISS. We were also going to have Lori from GFDL, but she couldn't make it today. Hopefully we'll have her at a future event. And for those who haven't been here before, the setup of this symposium is we have today we'll have two short talks, about 12 minutes each. I'll give you a 2-minute warning when we get to 10 minutes. I'll just unmute myself and say 2 minutes. We have some time for questions after each one, and then after the whole after the talks are finished, we'll have a general Q&A. And we'll probably wrap up a little bit early today just because we only have two talks. So yeah, if you have questions, you can type them in the chat. You can also raise your hand, we'll unmute you, or you can unmute yourself. And this, yeah, we have our executive committee here, and we have a list of previous talks if you really want to, if you really want to catch up on other stuff that's happened in the past. So yeah, Harry, if you want to share your screen and take it away.
Thank you.
That'd be great.
There we go. Is that working?
Yep, looks great.
Interruptions. There we go. Yes. So hello everyone. As Andrew said, I'm Harry Mutton and I work at the Met Office. And recently I've been working with Tim Andrews looking at how biases in climate model global warming trends are related to deficiencies in Southern Ocean sea ice evolution over recent decades. So to give a bit of motivation, and kind of this work is framed around the fact that observed patterns of sea surface temperature have differed between sea surface temperature patterns have differed between OGCM simulations and observations. So to kind of depict this, here are two plots I've stolen from Armour et al. 2024. And the top one is showing observed sea surface temperature trends between 1981 and 2014. And here we see kind of this marked cooling of the tropical Eastern Pacific and the Southern Ocean. Now, if we look at our coupled AOGCM CMIP 5 and CMIP 6 simulations over the same period, we don't get that pattern of warming. And this is important because these different patterns of warming impact feedback processes and then ultimately lead to biases in global surface temperature trends and emergent constraints. And this kind of disparity between AOGCM simulations and observations is true not just for sea surface temperature patterns, but also for sea ice evolution as well. And that is particularly true over the Southern Ocean. Hold on. Oh no, I can't move everyone's heads. So here we have a plot of Southern Ocean sea ice fraction anomaly over that period. And those different coloured lines are showing kind of values from observational data sets. And then these black lines are showing values from a large historical ensemble using HadGem3. And what we see is that in the observations, we saw this increase in sea ice over time, and that's despite the world warming. Whereas in our historical simulations using HadGem3, none of our ensemble members managed to capture that behavior. And so previously, people have looked at this kind of Southern Ocean cooling feature. Work by Sarah Kang and Yue Dong have focused on that, but more from the perspective of understanding how that impacts the tropical Pacific sea surface temperatures through teleconnections. But here, what we were interested in is investigating more specifically the impact that these sea ice biases themselves have on global surface temperature trends. So to dive into some of these results, so here we have a plot of net feedback and surface albedo feedback on the x-axis, looking from the years 1985 to 2014. And we're showing that for our large historical ensemble in these black dots, and also for a range of AMIT pi forcing simulations. Now, so AMIT pi forcing is a AGCM experiment with sea surface temperatures and sea ice prescribed from observations. And these different colored dots are showing the kind of impact of using different sea ice or sea surface temperature data sets. So the magenta ones are the AMIT pi forcing experiment that uses AMIT2 sea surface temperature and sea ice. The orange ones are the same, but instead have HADIS2 sea ice, and the cyan dot as well is showing is similar to AMIT pi forcing, but has had SST1 sea surface temperatures. So what this plot is showing basically is that all of our AMIT pi forcing type simulations, so these simulations forced with observed sea ice and sea surface temperature, have more negative net feedback and weaker surface albedo feedbacks. And they sit right at the bottom left of that historical distribution. And that is true also for a set of different CMIP6 models where we've done a similar analysis with the exception of MIROC6. So we're interested in understanding why kind of there's this discrepancy between AMIT pi forcing and our historical simulations. And one component of that is the Southern Ocean sea ice and surface albedo feedback. So here we are showing Southern Hemisphere surface albedo feedback on the y-axis and changes in sea ice fraction per degree of global warming on the x-axis. And across our large historical ensemble, again, we get this spread. And our AMIT pi forcing type experiments sit right kind of, with an opposite sign of sea ice change per degree of global warming and surface albedo feedback. And this kind of brownish dotted line is showing the observed values as well. So whilst our historical AOGCM simulate this positive surface albedo feedback and decrease in sea ice per degree of global warming, our AMIT pi forcing simulations show a negative surface albedo feedback and an increase in sea ice per degree of global warming in the Southern Hemisphere. And to kind of show what that looks like spatially, here we've got a zonal mean, so latitude on the x-axis, and lambda net on the y-axis. And we've got each of our different historical ensemble members showing this kind of positive lump in net feedback. And we have an observed value, kind of an observed estimate in this brown line, and then values from our AMIT pi forcing simulations in these other colored lines. And what we see is that none of our historical simulations managed to capture this negative spike seen in the AMIT pi forcing simulations. And we're interested in the impact that that has on global surface temperature trends. And to do that, we use a simple model that relates trends in global surface temperature to trends in global effective radiative forcing. So in this plot here, we've got effective radiative forcing on the y-axis and global surface temperature on the x-axis. And we plot each dot here is a year in the historical ensemble mean from HADGEM 3, and we've excluded volcanic years as well. So this relationship gives us kind of a simple model that helps us, well, it is captured by this equation. So delta F equals rho delta T, where rho is our climate resistance parameter, and that is equal to kappa minus lambda. And kappa is our ocean heat uptake efficiency, which can be estimated as the regression slope between N, so top of atmosphere radiation, and TS. And what this equation does is it gives us a nice way of relating changes in lambda to changes in surface temperature. So for each model, if we have an estimate of kappa and we have an estimate of F or trends in F, we can rearrange that equation to look like this. So delta T equals delta F over kappa minus lambda. And we get these curves for each model. And that gives us a nice way of relating net feedback. Notice here, this is minus lambda net on the x-axis. we can relate net feedback to global surface temperature trends. So we want to use this equation then and plug two different values of lambda that will help us understand the impact of our Southern Ocean sea ice biases on the impact of that has on global surface temperature trends. So firstly, the value of lambda that we apply is lambda net taken from our historical ensemble mean. So that's this black solid line averaged globally. And that will give us our historical net feedback and the global surface temperature trend associated with that. And then the second value of lambda that we apply is similar, but instead here we're going to substitute in our Southern Ocean values of lambda net taken from aim at pi forcing. So that's between these kind of two vertical black lines. We substitute our aim at pi forcing values into our historical ensemble mean. And when we do that, we get something that looks like this. So here our dots are showing the values taken from our historical experiment, so our historical feedback and the associated temperature trends using that equation. And then in our crosses, we have the values of lambda net and TS derived from historical simulations, but with the Southern Ocean net feedback substituted in from the aim at pi forcing ensemble mean. And what we find is that when we make that substitution, our feedbacks become more stabilizing, and our change in global temperature trend changes by about kind of 0.05 Kelvin per decade.
2 minutes.
Nice. And we kind of see that behavior is consistent across each of the models analyzed. So all the models are struggling to capture this Southern Ocean sea ice. And this kind of gives a nice way of indicating how that affects global surface temperature trends. And obviously, this is kind of making the assumption that all other processes are remaining unchanged. And in reality, kind of these changes will have connections to other areas and other processes. But it kind of nicely captures just the impact that this process has on its own and the impact that has on global surface temperature trends. Right, so conclusions. So to summarize, we show that there are large biases in Southern Ocean sea ice evolution between 1985 to 2014 between AOGCM simulations and observations. This difference in sea ice evolution strongly affects the surface albedo feedback. And then we show that this discrepancy in feedback leads to biases in global surface temperature trends. I think there are various kind of discussions to, the various other things to consider, such as the fact that since 2015, observed sea ice in the Southern Ocean has declined substantially. And whilst I think there is still kind of a discrepancy between observed and modelled sea ice, obviously this kind of more recent evolution will impact, how we interpret these results. But yeah, I think what we've done here is highlighted that there are obviously sea ice processes that our models aren't capturing that have happened in the real world. And that can have quite a substantial impact on global temperature trends. So yeah, that's the end. Very happy to answer any questions.
Great, thanks, Harry. Great talk. We have some questions in the chat already. Marcus had a question. I don't know if you felt that was addressed already, Marcus, or if not, do you want to unmute yourself?
Yes, that was addressed. Thank you.
Cool. And then Karsten said, do we understand what has caused the flip in recent years regarding the change in Arctic sea ice trends?
Yeah, I think there's been a lot of work that's tried to understand why sea ice increased over kind of this period that we've analysed. And there are a number of different kind of processes suggested, for example, stuff to do with ozone, or what are the other things, like Antarctic meltwater, and natural variability. And like, yeah, there's been quite a lot of different discussions that have kind of looked to understand it. I think in this work, I've tried not to be too much of an expert in, Southern Ocean sea ice evolution, and more kind of highlight the impact that it's had on global surface temperature trends. But yes, so in short, I don't really know a good answer to that question, but it's definitely an important thing to understand.
Great. And then Tim has a question, which I think is the change in lambda net looks larger than the change in the surface albedo feedback.
Yes.
If so, what other feedbacks are changing?
Yeah, so that's kind of this plot here. And the spread in the x-axis here is a lot smaller than the spread in the y-axis. So I agree, there's obviously many other processes happening. And I think it might tie into the work that Sarah Kang and Yue Dong have looked at, kind of how there are teleconnections with cloud feedbacks in the Eastern Tropical Pacific, or things like that. So there's definitely some related processes happening. Yeah, so I don't know if that addresses that question.
If it doesn't, Tim can unmute himself and say
Yeah.
something. Yeah, does anyone else have any questions they want to ask at the moment?
I guess I'll expand on that. You showed a zonal mean plot, and it doesn't seem like the tropical changes are particularly big, right? If I'm reading this correctly, the light orange line versus
Yeah,
black line. Oh, maybe that is a change. I don't know.
I think this plot only goes up to, I can't actually see the right side of the screen, but I think it doesn't go quite up to the tropics. So,
okay.
But yeah, I probably should.
I guess it's worth showing that plot for all the latitudes.
Yes, yeah.
Thanks.
I'll put it down actually.
Yeah, Vince, do you want to unmute yourself?
Yeah. Hey, Harry, hopefully you can hear me okay. I know you're focusing on the 1985 to 2014 period here. I'm curious whether you have any thoughts on sea ice changes going back to the pre-industrial period. I think Tim maybe has looked in the past about how differences in the sea ice data sets going back, much earlier, say to 1850, are pretty big. And I'm just curious whether you've thought at all about how these feedbacks could be different over a longer portion of the historical record as well. Thanks.
Yeah, that's a good point. I think, yeah, I suppose so. We've focused really on just the period that has good satellite observations that kind of consistent time evolving sea ice. And I think what is quite tricky calculating feedbacks kind of in the AMIT pi forcing simulation when there are massive discontinuities, as kind of you use a different way of, so if it's just in the AMIT pi forcing simulations, the sea ice kind of just remains constant for a long time, and then kind of a different observational data set comes in and it suddenly jumps. So those kind of discontinuities make calculating the feedbacks a bit tricky. I don't know whether there might be a better way of doing it rather than kind of calculating feedbacks as a regression, whether there's other ways that could be investigated. There probably are, and that might be worth looking into, yeah.
Cool, thanks.
Great. I think we should probably move on. And if people have questions, we can circle back to it at the end. Yeah, and next, Kate, if you want to share your screen.
Sure thing.
That'd be great.
Okay, can everybody see it fine? And hear me?
Yep.
Okay, all right, great. So I want to take a step back and kind of give a more meta talk on how do we know climate sensitivity, what do we not know, and how do we talk about it? So this is a paper I wrote with Mark Webb that's just been accepted at Earth System Dynamics. And it's really building on some of the lessons that we learned from the 2020 WCRP assessment that we were both involved in. And in that assessment, we adopted a Bayesian framework because why not? Bayes is awesome. And in this framework, the posterior distribution of parameters given the evidence is proportional to the likelihood of that evidence given some value of that parameter times our prior knowledge or beliefs about those parameters. And the thing to note is that our posterior estimates depend on a lot of stuff that's either uncertain or debatable. So first, we have to establish, what do we mean by evidence? What evidence are we using to constrain the parameters in question? So in the assessment and going forward, we have multiple lines of evidence that can constrain equilibrium climate sensitivity. We have the fact that the climate has been in different equilibrium states in the past, most recently 21,000 years ago in the last glacial maximum. We've got recent history where we've emitted a bunch of carbon dioxide and the Earth has gotten warmer. And then we've also got sort of process-based models and basic theory. And because the strongest constraints came from the last glacial maximum in the past assessment, that is what I'm going to zoom in and focus on today. Now, in a Bayesian analysis, the real math generally comes in via the likelihood function. Basically, how likely is this evidence that we have given some value of the parameters? But what is this likelihood and what are the parameters? And both of these depend on M. They depend on the model that we use to interpret the evidence. So what do we mean by model? Well, in this case, I think it's required by law that every single ECS talk has to have this simple energy balance model equation here. But for example, this is a way that we can interpret the evidence. And this simple energy balance model has one parameter, which is the net feedback lambda. Now, other models are certainly possible, and I will talk about those a little bit later in the talk. And finally, our estimates depend on our prior knowledge or belief about those parameters. So what do we know, for example, about the net feedbacks before we even go in to do this analysis? Well, we know that they're probably negative because the climate is stable, we exist. They're probably not infinite because physics exists and energy is conserved. And they're probably not zero because climate sensitivity is not zero, it exists. And our choices about all of these things, what is the evidence? What is the interpretive model we use for the evidence? And what is our prior knowledge of those model parameters? Our choices about all of these things will shape our end result. And I want to stress that choices are inevitable. No tractable scientific analysis that has ever existed can avoid making decisions. And you can't avoid making these decisions by getting rid of the Bayesian framework, because frequentist models also require you to make decisions. They just make those decisions implicit and hard to understand. We're going to argue that Bayesian methods provides tools to transparently and fairly incorporate expert judgment. So how do these choices shape our results? So first, think about uncertainty in the evidence. So in the WCRP assessment in 2020, we used particular estimates for the cooling during the last glacial maximum and the radiative forcing that caused it. So this is the joint probability density function we used. But other estimates exist, other assessments are out there. So for example, Tierney et al. 2020 published an estimate of cooling that was much larger, about 6 degrees as opposed to 5 degrees, and temperature and forcing estimates that were much less uncertain. So clearly here, although there is considerable overlap, these are very different pictures of what was happening 20,000 years ago. So how do we go about converting these evidence estimates into a likelihood? So remember that simple energy balance model? Very clearly, this model defines a line in evidence space and will define the likelihood as the probability mass along the curve defined by the line for various values of lambda. So using this simple energy balance model, this leads to very different likelihoods for the net feedback lambda, depending on which evidence we use. But it gets worse than this. This is not even the only reasonable model that we could use. So suppose we believe that climate sensitivity is state dependent. The feedbacks in a hot climate are not necessarily the same as those in a cold climate. We might want to include a state dependence parameter alpha that reflects this. And clearly the likelihood depends on the evidence, the model, and the value of the model parameters. Now, there's also uncertainty in the prior knowledge we arrive at this analysis with. So with multiple parameters, alpha, the state dependence alpha, and the feedback lambda, the posterior is a joint probability density. And basically, if we don't know anything to begin with, our analysis will tell us nothing. If we believe the state dependence is just as likely to be minus infinity plus infinity, if we believe that the feedbacks are just as likely to be positive or negative, we're not going to be able to make the evidence tell us anything. And this is really obvious, right? We have to know something about how the past relates to the present in order to use this information. We need to know what are reasonable values of state dependence, what are reasonable values of the feedback lambda. So basically, the more we know, the more we know. The priors can really substantially constrain the posterior distribution. And the point that I want to make is that the net result of all of this is wildly different estimates for climate sensitivity, depending on the priors, the model, and the evidence. So where do we go from here? We want to leverage the community of estimates, including pretty much all the folks on this call. We want to make it automated as much as possible because I'm lazy and I don't want to do this again. We want to be able to update our conclusions with new evidence that arrives. We need to account for all sources of uncertainty. We need to incorporate expert judgment transparently, fairly, and at, I would argue, very clearly defined points. And we need to make this open to all experts, no matter how wrong or stubborn or unpleasant they are to participate. So how should we handle evidence uncertainty? I would argue we should handle it Bayesianly, if that's a word. So for example, we've got not just the estimates in the WP assessment and Tierney et al. 2020, we've got multiple estimates of the cooling during the last glacial maximum from proxy-based reconstructions, lots of them, from PMIP model runs of several generations. So we propose to handle this using a Bayesian meta-analysis, where experts have to specify their prior on the quantity of interest. So in this case, the cooling during the last glacial maximum. And importantly, the inter-study spread, tau, which determines whether we're using a fixed effects versus a random effects model. And these priors really, really, really matter. So for example, if we start out as our prior, the estimate reported in Tierney et al. 2020, last glacial maximum was 6 degrees cooler with relatively small uncertainty. Now, if we believe that all the reported estimates of LGM cooling differ only by measurement noise, if we use one of these fixed effects models, then our initial belief will be treated as an outlier and it will be updated accordingly. But by contrast, if my prior belief is the same, but I believe that there is substantial structural difference in the published estimates, my prior is not going to budge very much. And this is where we need the expert community to step in. This is essentially, the Bayesian meta-analysis is essentially a way of automating literature assessment. What do we as a community believe the evidence to be, and how do we incorporate this new information? Now, to handle model uncertainty, we go into more detail in the paper, but essentially we recommend that a small group of organizers of any future assessment, any IPCC estimate, whatever, need to clearly specify the interpretive model we used to interpret the evidence, not just paleo, but historical and process-based as well. Are we going to include the possibility of state dependence, of pattern effects? Are those pattern effects modeled additively or multiplicatively? Are we going to include separate forcing efficacies or fold them into the pattern effect? What is the transfer function from Earth system sensitivity to equilibrium climate sensitivity, et cetera, et cetera, et cetera? So once the interpretive model has been clearly specified, experts participating in the assessment can then step in and specify their priors on model parameters. Do you not believe there is a pattern effect? Fine, set your prior on it to be a delta function centered at 0. So experts will enter here only via specifying the priors on the parameters. And finally, we're recommending that once this framework has been laid out, expert judgment is elicited only via prior specifications. So this means that in this particular framework, experts have to specify their priors on these hyperparameters for the evidence meta-analysis. Basically, what do you think the evidence is? And what do you think about the state of the literature? And then priors on the model parameters. What is your prior knowledge of the feedbacks? What is your prior knowledge of the pattern effect, state dependence, et cetera, et cetera? Now,
2 minutes.
Great. I know this will come as a surprise to everybody, but sometimes experts can be aggressive or wrong or overconfident. So how do we handle the priors of these folks? So we're arguing that the aggregate prior should be an average of the expert priors, weighted by how well those agree with the evidence. And we provide the math to do this in the paper. So you can see in panel A, we've got 2 experts, expert A and expert B, who both have sort of reasonable priors. Updating their priors with the evidence causes them both to agree with one another. In panel B, you've got expert A, who has the same prior, but you've got expert C, who is extremely, extremely, extremely confident that climate sensitivity is very, very, very small. Now, how do we prevent this expert with their extremely restrictive prior from biasing the outcome? Well, when we use this weighting, we arrive at essentially the same posterior as before. So I just kind of want to summarize and start a discussion. The best way we think to do this is for a small group of organizers to collect published estimates, to specify very clearly the interpretive model we use to interpret that evidence, invite experts to participate, and then turn the crank on this. Experts should specify their priors on the evidence and the interstudy spread, specify their priors on the model parameters, the feedbacks, the state dependence, the pattern effect, and then go away. And so, you know, this sort of reflects the state of our understanding, the way that we would do it if we had to do it over again, and possibly the way that we should collect this uncertainty in the future. So thanks for listening.
Great. Thanks, Kate. Brian, do you want to unmute yourself?
Sure, thanks. Thanks for a nice talk, Kate. How do you get all of those strongly opinionated experts to stop arguing about the choice of interpretive model and thereby give you the actual expert information you want in this exercise?
Yeah, that's a great question. So there's kind of 2 ways to do that. One is to, for the choice of interpretive model to be kind of this massive, unwieldy, jury-rigged thing, where you have a bunch of parameters, you account for everything that could possibly enter in trying to translate evidence into an estimate. And then folks who are like, I don't believe that this parameter is a thing, set your priors to be a delta function. The other option is to use Bayesian model averaging. We go into this a little bit in the paper, but basically there are ways to weight models depending on how well they explain the evidence. And you know, there's a whole range of different methods for model criticism. And I should be really clear here, when I mean model criticism, I mean interpretive model, that's statistical model, not necessarily GCMs. There's ways that we can assess models based on how well they make estimates from multiple lines of evidence agree, how well they explain a particular line of evidence. So it's quite mathematical, but we go into it in the paper. But again, that is dependent on the priors that we have on different models, right? So if I believe that this model is correct and this model can never be correct, then I'm never going to update my priors. I can weight it all I want and nothing is going to change. So, you know, very, very quickly, we go down, it's turtles all the way down, right? You know, level upon level upon level. And eventually we are just going to have to draw the line and make some statements, make some decisions. And we just need to be careful about being explicit about how we're doing that.
Thanks.
Kevin, do you want to unmute yourself?
Yes, thank you. I'm looking forward to reading the paper in more detail. And what I want to explore a little bit more is the evidence side of this story. So in principle, you could calculate the information content associated, given a model, given an interpretive situation, that this evidence brings to the table. But the choice of evidence is actually quite capital in the selection and how you, you know, if you have more evidence or the type of evidence, the correlation or uncertainty in that evidence becomes an important factor in the robustness of the conclusions, irrespective of the level of, say, expert knowledge being brought to the table in the priors. So could you just elaborate a little bit more on how you think about both the way in which multiple lines of evidence are combined, which I think you alluded to, and maybe even possibly how the outcome of the analysis, say for climate sensitivity, could lead towards insights into what new types of evidence should be searched for?
Yeah, thanks a lot for that question. That was actually something that we were really hoping, those conversations we were hoping to spark with this paper, because theoretically, what any assessment should do is not only report the current state of knowledge, but also provide a guide for future research, right? If we look at the evidence and we say, oh my gosh, like the reason we don't understand XYZ is we have no idea what ice sheet forcing was during the LGM, then, that's a place that we can go and maybe get more certain about that. In terms of what should we use as evidence, how do we understand the information that each line of evidence or each individual piece of evidence is bringing? Kind of the beauty of Bayesian methods is that you can use hierarchies, right? So you can insert kind of an arbitrary number of hierarchies. So you can say, all right, well, I've got a lot of evidence for the last glacial maximum cooling from different proxies. Okay, now let's zoom in and let's look at this proxy evidence. While proxies are being made into temperatures using particular choices, a forward model. Now we can sort of zoom in and we can apply the same framework to that level of the hierarchy, and so on and so forth. And theoretically, like you can do that for all of human knowledge. You can do that for all of, particular scientific knowledge, but you have to truncate the hierarchy somewhere in order for your analysis to be tractable. So I guess my answer to your question is twofold. One is the same as the answer I gave before, like you got to draw the line somewhere, make it really clear where you're drawing the line. And the second is, you need to communicate this stuff. You need to communicate the results and the uncertainties in such a way that leaves the door open for future research and allows you to update very quickly that posterior given new evidence.
Thank you.
We have two questions/comments in the chat. So David Sexton says, one thing to watch for is when the evidence lies in the tails of the prior predictive distribution. If the evidence is in the tail, then often the Bayesian analysis can be overly sensitive. This can be diagnosed, so it might be used to tell the expert their prior is not consistent with the evidence, which I think is something similar to what you were touching on then.
Yeah, can you clarify what you mean by the Bayesian analysis can be overly sensitive, like compared to what?
You're muted, David. Oh, okay. Maybe we can go to Christy's question while David is sorting out his mic. Christy, do you want to read your question? Or...
Sure, if you can hear me. I have a weird setup.
Yep, I can hear you.
This is sort of an ill-formed question, but isn't the choice of prior sometimes a statement of belief on the interpretive model? Like if we use a flat prior on lambda instead of S, isn't that really a statement on the fact that we think that the climate system operates through feedbacks rather than through a bulk sensitivity? I don't know if you have any thoughts on that. I struggle with that distinction.
Yeah, and I think Mark and I struggled with this for literally years. And the conclusion we came to, and maybe Mark, if he's on the call, can jump in. But the conclusion we came to is that these boundaries are fuzzy, right? Like there is, saying something is evidence uncertainty versus model uncertainty versus prior uncertainty. Well, the boundary between like prior uncertainty and model uncertainty is fuzzy because the model is specifying the priors. And so, in your case where we use a flat prior on lambda instead of S, is in this, basically that's saying the model in which we have a parameter S and therefore something to put a prior on is a different model than a model in which we have lambda and something to put the prior on as lambda. So we go into this a little bit in the paper. We actually worked out the exact mathematical difference, and I'm happy to go into that later with you. But the short answer is that it's a fuzzy gray area between what is prior uncertainty and what is model uncertainty.
Cool. David, you look to be in a better setup.
Yeah, I'm in a better place now. Can you hear me?
Yes.
Yep. Yeah. So I was just making a comment based on my own experience. It's although you shouldn't use the evidence to inform the priors, it's good to check with the evidence that your priors aren't going to be overly sensitive to the actual likelihood update, because you can get just strange answers. It'll always give you an answer, a Bayesian estimate, but it could be a poor answer. So there are ways of checking. So you could report back to the expert and say, actually, you've gone for this prior, but that's going to create a very sensitive Bayesian analysis, and can you adjust it? So
okay. Well, in the future regime, we will make you responsible for informing the experts that their priors are bad.
Oh, I've got a diagnostic for it. It's okay. It's all objective. But I can tell Mark certainly, because he's probably down the office somewhere, so I can let him know. He's actually on the paper where we did this. So
great. And Christy, I think you do know who Expert C is.
Cool. Well, we got a few more minutes if people have more questions, either for Kate or for Harry. I guess while people are maybe thinking, I have one broader question, which is just like, so Kate, what you presented now, how does this, as someone who doesn't know the details of the WTRP assessment, like what of this wasn't happening? Because I got the sense the Sherwood paper, that is a Bayesian framework. So is a lot of this just happening implicitly and a bit more messy, or?
Yeah, I think messy is a kind word for it. A lot of this is happening in rooms. A lot of this is happening with, arguments between personalities. A lot of this is herding cats, as is every scientific assessment with, bright people who have strong opinions. And in order to make something that everybody understands all of the decisions that went into it, and the point at which those decisions entered. We felt like it was important to present a framework in order to try to automate that and in order to try to make it as transparent as possible.
Cool. That sounds good. Vince, do you want to go ahead with the question?
Hey, Kate. Thanks, Andrew. You went through the motivation from the Tierney et al. 2020 LGM comparisons pretty quickly, but it seemed like a lot of the uncertainty was from the state dependence parameter. I'm curious whether you thought, you mentioned pattern effects, but I'm not sure if you thought about them at all with the paleo evidence. So just curious whether the paleo pattern effects for the LGM shows up at all in this paper, or if that's not been on your radar yet. Thanks.
I mean, I think it's really important, and I am completely convinced that there were pattern effects in the LGM. I just, my prior is that the pattern of cooling is very different from the observed and predicted pattern of warming, and that is radiatively important. So my prior, although we don't address it in the paper for simplicity, but my prior is that there's certainly a pattern effect in the LGM, and I think there is lots of evidence to support that. In terms of, and that basically means that an organizer of a future assessment or a future IPCC or future whatever, I think should specify a pattern effect in the interpretive model for the last glacial maximum. Where it comes to the Tierney et al. Paper, and I don't mean to pick on any particular paper, I was just using that as an example of a LGM estimate that was quite different from what was reported in Sherwood et al. you know, it's basically, we're saying something really quite obvious, that if you think the last glacial maximum was 5 degrees colder and forced by a radiative forcing of 9 watts per meter squared, you're going to get very different estimates of climate sensitivity than if you think it was 6 degrees colder and was forced by 6 degrees of, you know, or 6 watts per square meter of forcing. So basically, different estimates of the evidence will lead to very, very different estimates of climate sensitivity, even using the exact same model. Now, when you incorporate alpha, when you incorporate state dependence, your results get even more uncertain.
Cool, thanks. Yeah, just in case you're curious, we did some work on the LGM pattern effect. There was actually a talk for this, and I think it brings the lines of evidence a little bit closer together. So you might be interested in it. I'll shoot you an email. Thanks.
All right, cool. Well, thanks everyone. Looks like we should probably wrap up now. But yeah, thanks to the speakers again. Thanks to Harry. Thanks to Kate for 2 great talks. And we'll see you next month.